whatever they are, those are all function calls. And you work your way from the inside, outside. That's how you read that, right? So we're going to look at this. If this is a series of functions, then it doesn't matter. Sometimes they're a lot more complex than this, and they're a lot more cryptic. In this, what's happening first? If I was to look at this right here, what happens first?
Range.
Range. Range happens because it's the thing that's the most inside, right? And that's called, it's just strict evaluation. Range is going to happen first. After range does its work, it's going to give its work to what? Right. Sum has no idea what is happening in range. And it doesn't know anything until range is complete. So range is all done with everything, and then sum gets its work, right? So now sum is going to get the work, and sum's work is going to be values, right? That's all we know. It could be an array, it could be an object literal, but it's going to get some kind of value back. And now we have one more function in there. Anyone know what the last function is? Console log, right? That's a good one. Okay. So console log is interesting because it's actually, log is the name of the function. Console is the name of an object. So when you call console log, you are in fact calling a function, right?
So
okay.
It's a method.
That's right. Yes, it's a method. And I think we get to that in the next class, actually. Which, by the way, when we get to the method class, I get to answer the question that everyone has asked me in every class, which is what's the difference between the fat arrow syntax for functions and the other syntax. I said one thing early on, and I think it's there's something on the internet. It's called the Streisand effect, and it's if you try to tell people, you try to ignore a piece of information or hide a piece of information, you say let's not talk about it. It's the one thing everyone wants to talk about. Okay, so moving down. Let's take a look at it. We're going to see where he's going with it. He has, by the way, this is a really horrible description. I hope no one focused on that one too long. Okay. So now we have this for loop, right? And again, this for loop is very, I mean, the moral of his long story is that for loop is very verbose. It's very explicit about what it's doing. So he's creating a function here called repeat log, right? And repeat log is a lot easier because repeat log just takes a number and it obscures the whole counting variable and the conditions and all of that type of stuff. And all it does is do console.log on every number from 0 to that number you give, right? So if I say I'm going to create a function called repeat log, I give it 10, it's going to count 0 to 10. That's very simple. You don't worry about the underlying implementation. You can use that in other parts of your program, and all you see are the words repeat log. You look up here, this for loop, that for loop is much more mental processing time. Every time you see it, you got to figure out what it's doing, what the terminal condition is, what's happening, it's getting incremented, what is it doing inside, it's calling console.log, it's just more work. So the functional method of doing this tends to produce shorter code. Okay. So here's the very typical example, and that's repeat. So repeat is just like that thing we just created, which was that repeat log. But repeat, rather than calling console.log, is accepting an action, right? And here's the thing. A lot of people are going to have a problem with this the first couple of times they see it. People are really good at determining the categories of objects, right? They're really good at that. They have a harder time thinking about actions as being something that can be passed around.
Right, because it looks like the code, it looks like the body.
Right, yeah, and it's something natural.
But here it is stuck in with the paradigm.
Yeah, you would almost never say in any form of, you would almost never say in English, pass me the run. Or,
But if you can do it like this, why doesn't everybody do it? Why bother having the parameters here, and brackets or parentheses or whatever, and then having the body code and some other, put it all together?
So functional programming, backstory, came out in 1960. It predates C, it predates most imperative languages, it predates object-oriented language. It is old as shit. I'm trying to watch it. I'm sorry. Come on in. It's a very old method of getting your idea across. It's also a very difficult method in which to think and model a problem. In fact, Brian Kernighan, who actually invented C, said he can't think like this. He just threw up his hands and said, I can't do it. A lot of people can't model problems like this. To answer your question, why isn't everything done like this? It's quite simple. It's like speaking another language. I've tried many times. It's very difficult. Everyone thinks I work here and I can sign this. I don't know. Can I sign this? I have no idea. I'm tempted to try it first. Yes, that's absolutely not what I want to do. I was thinking if it makes your job easier, I'm happy. But if it means that I'm buying everyone pizza today.
It'd make my job a lot easier if you signed for it every time.
All right, so the bottom line is I want everyone to understand that it is more difficult to think in the functional paradigm for many people. Some people have determined or have concluded that they can't do it or it's not worth their effort. We can call them quitters, whatever. But the reality is that one of the reasons why this didn't take off is because it's much more difficult for people to model problems like this than for people to essentially model problems like a to-do list in a grocery store, right? Go to the bread aisle, turn to the right, pick up a carton of bread, go, that's very easy. We're used to that. This is much more difficult. But you can do this type of stuff. So we are creating a function here called repeat. Repeat is taking a number and it's taking an action. And all it's going to do is very simple. Right here, this is the guts of it, right? Action is a function. Functions do stuff. You're going to call that function you provide to repeat, and you're going to give it a variable that represents whatever iteration it's on. And that's it. So here, we hard-coded console log. We said this is easy. Repeat log is taking a number, we're iterating, and as we iterate, we're calling console log with that number. That makes sense. This, we lose a lot of people, hopefully not here. But in this, we're taking a number, and we're doing the same thing. It's the same loop. That same for loop on both sides of this is the same. The only difference is we call action, that function, with the variable. So all we're saying is in this form we can call something that's not console log with it. And it looks just like that. And it looks like that because console log is a function. And you can give it any function. It's just going to call it and provide the argument. All right, we had pizza. I don't like your pizza get cold. That's some kind of atrocity. Let's go eat it. Unless it's pineapple pizza, in which case you should go right to the trash can. That should actually be lead. Don't use var. I'm old. Don't do that. It's not good. We don't use var in this class. You want to know what A can do? What do?
Tab.
Slam on tab, right? So we just hit tab a couple of times like that. And it does this thing called tab expansion. It shows us all the different methods. These are things that you can do to A, or things that A provides for you. Some of these things we're going to be covering today, like you'll see reduce in there. This is a big thing today. We're going to cover that. There's also for each. We're going to cover that today. And that, we're going to cover that today.
Is this just in game?
So this is actually Node. Node is server-side JavaScript, so you can download that and install it, and you can test JavaScript outside of the browser. So you have JavaScript inside of the browser, which makes the monkey dance. You have JavaScript outside of the browser, which you can use for everything for systems administration or not. Right? Inside the browser, Angular, React, that kind of thing. Outside the browser, Node. Systems administration, WebSocket servers, web servers, all of that kind of stuff. Yeah. And there are a couple of chapters on Node, and we'll probably cover a little bit more of that. All right. Anyone have any other questions? Chit chat, topics, random questions? While we finish pizzas? Yes.
Yeah. Well, it's not about this. It's about Wi-Fi. Do you know which Wi-Fi name?
I do, actually. I can get you that, too. So here's what we do. Here's something that's great about Linux. Linux doesn't pretend to keep your Wi-Fi password secure because it actually has to know it. So I just come down here, and then I say Wi-Fi security, show password. It's that thing. Oh, there you go. It's right there. So it's 2550 guest, and then that's it.
That was just a return from
Okay.
asterisk.
Awesome.
Lowercase numbers.
Go over a little bit the compile time, build time, load time, run time scenario for JavaScript.
I can. I can give it a shot. Some programming languages have a concept of compile time. Right? Has anyone heard of compilation?
Yes.
Everyone's heard of it, right? Compilation is when you give something text, and it takes that text and it makes from that text byte code or machine code which the computer can execute. For some things, it's
both outputs are satisfied by the term compile. But doesn't the bytecode have to be further compiled before you can get to assembly code?
Depends on how you're compiling it. When you compile a C program, the end result is machine code. There's no assembly, there's nothing higher level. You just get machine code. You get
Okay, but can you get, well, bytecode is not true code, right? It's somewhere on the way.
That's right. So JavaScript has different steps of compilation.
That's what, can you tell me?
Yeah, but I want to keep it kind of brief. Okay, so when you give JavaScript code, it compiles that code into bytecode, right? Okay. And it will optimize that later as it sees fit. But none of that is exposed to the user. So the whole idea of it is how it's internally working. You won't see it, you don't need to know it, it's all a trick. It's a magic trick.
Why do they carry on all the time about something being available at runtime, or I don't even know how to
In
say
JavaScript
it?
they don't. In some languages they do.
Whoa.
Compilation is different. That's a language specific thing.
Wow, so we don't really have to know.
You don't have to know it.
Oh. That's the way they said that.
All right.
Yeah, you see the PS.
You get a code.
Just like
Where we left off, we just covered repeat. Repeat is like the previous function we did, except it takes an action. This is the thing that makes it higher order. Because it takes an action, you can model your program like that. Right now we actually have a looping construct, and we define what we're doing in that function that we provided. So we have this function, action. We can define that, and then we later get this call here. Now, here's something that they're not telling you. This is what you would see in JavaScript, and we're going to ignore a lot of details, but in JavaScript we call this a callback. Has anyone here heard of a callback? Okay, we have quite a few people who have heard of a callback. A callback is this method of modeling a program where you provide something which that function will call, right? And here's the catch. The reason why we do a callback, and you're going to see this a lot more later on in this book, but we're not going to get into it thoroughly today, is that when we call repeat here, right? Later on, repeat calls action here. And I'm highlighting this so everyone can see it in the event you don't see my hand waving around in the air, and that doesn't make sense to me. So we have, now I'm trying to get, okay. One of the things I'm finding to be tremendously difficult with this is this code box gets big when I click it, and I can't make it get small again, which means it doesn't sit in the middle of the screen. Reset sandbox, Revert to the page.
Deactivate editor, the last one.
That's why I like it. I can't figure this stuff out. King of user interfaces. There
Yeah.
we go. Okay, so now we can make it bigger so everyone can see it. Dun dun dun. Scroll down. We have this action here, right? Hopefully everyone can see that now. This action, we give it to repeat, and repeat calls it. When we do this, we make for this example, we're showing you that when you call repeat, it's doing this loop and it's calling action, but nothing is happening in between, right? In between. That means I'm trying to think of a way where I can do this without getting too deep into it right now. Action is being called inside of repeat, and nothing is happening to slow it down. Think of it like that. in JavaScript, a lot
Because
of
it doesn't have an argument? Because it
because
doesn't know what argument?
it's not going out to a network, it's not drawing on a screen, it's not doing that type of thing.
But also, it doesn't know what action is yet, because action is just a parameter, right?
Right, but the notion of a callback is a lot of things you'll do in JavaScript take time, right? Because you have things that slow it down, like network operations. Go out to Google and get me the result of this complex Google Maps query, right? Now you have to make a connection to Google. You've got to ask Google what to do. Google's going to think about it. It's going to do the results. It's going to send it back to you. There's time that's being spent there, right? Now the deal with the callback is you provided an action, and then it doesn't do that callback until it gets the result back from Google, right? So you say, here's my callback. When you get the result back from Google, do the stuff with that result, right?
But you can't do it with action, because action is just a
No,
parameter.
Action is a callback, but I'm telling you, this is where this is useful. Let's ignore it. Let me just get it. I didn't want to go too deep into it. I wanted to give you like a high-level overview
What
of
they
it.
call it with repeat 3 console logs, right? They are the two end and action are parameters. They have arguments. They get past real arguments. How can it do anything before it has action anywhere? Then it can do something before it gets 3.
It can't in this case. So what Peter's saying is that if you look here in this repeat.log, nothing is happening between it. You can see it, right? That's a valid point.
Well,
Nothing is happening.
That's a whole different piece of code, by the way.
Okay. Look, but this is.
I'm sorry. Okay, forget it.
I know. I didn't want to. Look, here's the actual code, the repeat thing,
there.
right? Peter's saying nothing is happening in between here to slow it down. That's a valid point. I'm saying that's not often the case. If action is a callback, frequently something will happen that slows this down. Like here, it's gonna, like right in between this, it'll do something like, okay, make a connection to Google, right? Issue this query to Google. All of that stuff is going to be slow. And what you don't want to happen is, when you're making that connection to Google, you don't want all of your JavaScript to be slow. So you provide the function a callback, and when all of that stuff happens and it's done, it calls you. And because it does that, it breaks this control flow. We're going to go into this more later, but I'm showing you that right here we're providing an action at the very end, and we're letting the function repeat call that action. This is simple. In JavaScript, you will see this all the time in the form of a callback, all the time, right?
When the first, that piece of code right there, is action, is the second parameter, action is a function, is it being run right there without a parameter? And then when it gets in there, it's getting the parameter from I?
No. It's actually, it's saying what's happening here is when you give it n and you give it action, it's going to make the first iteration of this loop. I will definitely be set to 0, and it's going to call action with I set to 0, all at the same time.
Oh, I see, it sets up the parameters, but nothing really happens right there at the beginning of the function, like.
Nothing happens until it calls action.
Got it.
That's right. It's just, it's starting to set up I and increment I. Okay. And we will go a lot more into this callback thing much later. It gets slightly more complex than we're going to do today, but what I want to say is that this action piece, this idea that you're passing in code, which that function will call, that's where you see this everywhere in JavaScript. Okay. Coming down. Now we know the trick here. But okay. So now what we're showing is this concept of what we can do with this, right?
Wait, the title of this chapter was higher order function. Are all higher orders callback another way to say higher order function, or they're not? Or is that a callback's a subset, or what?
Precisely. Callback is a subset.
Okay.
Higher ordered function is any time you're essentially passing a function into a function, right? Callbacks are one method of doing it. There's a lot of others, right? And we're going to get into all of them later on. Okay, so here's what they're doing here. And the catch here is they're showing you that, remember in the first one, we were passing in for the action console.log. we started off the function repeat, right? Let me see if I can go back up at the top. And in repeat, we're essentially modeling this. So repeat log calls console.log. We move console.log out, and now we have repeat, which takes an n and an action. Now we're providing to n right here, we're providing to the action right here, console.log. You see this? That's the kicker right there. And what they're showing you is, when you have this piece for action, you can provide any function. Scrolling down, what we're actually doing here is we're using this fat arrow notation to do what? Create a function. That's exactly right. The fat arrow notation creates a function. Right? Would you like to explain what this function is doing right here? The function that we're creating? You what? That's exactly right. So we have this thing up at the top, labels. Right? Now we used a term earlier on, and that term was scope. Right? Labels is not scoped into repeat. It's outside of the curly braces. Right?
Got to count down.
Count down.
And it'll count down to eternity and give you an error.
Count down to eternity. Maybe. Okay.
Oh, yeah.
Jared, what do you think? Is it going to count down to eternity?
It's
That's right. Okay, so there's no terminal condition in this, right? If you don't have a terminal condition, you're going to do exactly that. You're going to count down to eternity. Actually, truth be told, computers don't do eternity well in any way, shape, or form. What it's going to do is do what they call stack overflow. And that's going to blow up in a really humorous way. You'll see that error a lot, right? So if I say my loop equals 10, right, that's what the stack overflow looks like, right? And essentially it's saying I can't keep calling myself because every time I do, I need more of something, and now I'm out of whatever I needed, right? So let's go ahead and fix that. Okay.
Can you tell how big the stack got?
Yeah, the stack got big enough to do 16,028 iterations, because I started at 10. So that's how big the stack got. And you can actually, you can custom compile that stuff if you're building nodes. I mean, it's just how much do you want to waste? If your function's calling itself, 16,000, 100 times, you're probably doing something wrong. Some languages do this really well though, because like I said, they're writing loops using functions. In JavaScript, we don't really do that. Okay, so let's write another loop, right? And let's fix it this time. So I'm going to say here, function, my loop fixed, right? And I'm going to give it n. I'm going to open up a bracket, brace. Okay, and let's go ahead and write it. So what I'm going to do here is I'm going to call it. We're going to say, we'll fix the problem. If n equals 0, right? We'll do 3 equal signs so no one kills me. Return, right? Now what I want to do is I want to call my loop fixed n minus 1. And then I want to call console log n. I'm going to end it.
What's going to be returned?
That is still bad. Part of that is my fault on that one. Let me see here. Okay. Function, my loop. Actually, you know what?
Let's show how bad.
Let's show how bad it is. Yeah. Okay. So, right away, he said it was bad, and he's right. Why is it bad, Ed? Tell him the reason.
It's bad because if you start with 0 or a negative number, you're again on your infinite stack destroying loop.
Okay, that's not actually why it's bad, but that is a valid reason. That it only works over a certain domain. There's a bigger reason why it's bad. Does anyone know the bigger reason why it's bad?
You're recursing before you print the n. I'm not sure what that's going to do.
Okay, that was intentional, right?
Yeah.
So that's the effect I wanted. Does anyone know the third reason why it's bad? One more shot. JavaScript doesn't return anything sensible implicitly. This is not returning anything, right? So one of the big problems is that it's going to recurse and it's going to do something valid, but normally you want to return something sensible, and I'm not. So that's actually the real reason why it's horrible. Now, you identified something that was really valid in there, right? You said, I'm printing out after I return. What is that going to do? Jared, what did you say the first loop did?
It was infinite.
Well, that was the correction.
It was counting down.
It was counting down. what do we expect this loop to do when you put it after?
Count up.
It'll count up.
Yeah.
It's going to count up, right? So I just wanted to show you that. That's actually the effect that I was going for. It's that you have two options here when you declare it. I'm going to actually try to use this thing a little bit more so people on all sides of the room can see me. If you put the console log after the call to recurse, right, then what it's actually doing is it's going to do that after the recursion is done. So let's go through it. We give it 10. 10 is not equal to 0, so it's going to call itself with 9. Right? Now it can't do anything until that function returns. What is it going to do when it has 9? It's going to call itself with 8. Then it's going to call itself with 7. All the way down to 0. Then it's done. Now what does it do? Well, now all of these functions get to work their way back out of the onion. And now we see working that way outside, right? They're going to start returning whatever they were given. So if you put it in the front, as the recursion goes deeper, you have that work at the front of it that's going to be done. You're going to see 10, 9, 8, 7, 6. If you flip it, you're not going to see anything until recursion is done. Then you're going to see 1, 2, 3, 4, right? Because those functions are returning. So that's how I think about it in my head. I think if we're going in, before we call that, my loop fixed, right? Before we make this call, we're going in, we're recursing down, we keep calling itself, and we're doing work every step of the way. In this one, we don't do any work until we fit the terminal condition, and that stuff starts to return. Then you're doing the work as you go out, and they're all returning.
So let's say your like the n that you passed in is 16,000 something. So would you go 16,000 levels deep before you start printing anything?
Precisely. And this is a huge thing in functional programming. In fact, this book wasn't going to get into it, and neither am I, but you actually have these, you call them left folds and right folds, right? So if you actually pick a real functional language, not JavaScript, but something where you see this stuff often, you will see exactly that. And that's something that you'll have to consciously think about in functional programming. And welcome to the wonderful world of high-ordered programming. If that's really complex, it is. It's only complex the first 200 times you see it. After that, it's smooth sailing. So good luck getting there, and then it's a lot of fun. Okay, so there's your kind of warm-up. We did a little bit of recursion before. Now we delved even deeper into it, and we talked about doing work on the way in and doing work on the way out. And I only thought of that because Jared had suggested counting down, which was correct in the last one, by the way. Right? We just didn't have that terminal condition, and I wanted to throw a loop in there for this one. Okay. So, let's have fun. Okay, this book has a lot of, like I said, I'm not really fond of the examples because they're pretty complex for showing concepts, right? In this one, he's actually talking about encoding in a file, which is a horrible example, and we'll follow it through. So he starts off and he's showing you here, this is a basic loop, right? Nothing special there. And he's saying, look, this is how we have done it thus far, but we can do it a different way, right? And he's showing you this is some of the problems with it. It's that if that's how you're counting, you're summing up all numbers that are less than 10, then perhaps that's more complex than a syntax like this, and I would give it to him, right? And this kind of stuff, this domain, it's accessed by repeat. So that means that when repeat is done calling, and in between repeat calling, that value will persist. It doesn't go away. So we have a function here, and in that function, we take a value, I, and then we push on to this labels that value. That's it. Actually, we're pushing on the string, unit, and then we're pushing on the result of the increment of that value plus 1. So if we see here what repeat is doing, repeat is going to execute 5 times, and every time what it's going to be doing is it's going to get a different value. It's going to start off with 0. It's going to go to 1, 2, 3. Those are going to be the values of I, because if we look up here, right, to the repeat function, you can see that the repeat value starts at 0, and until it hits the value of n, I gets incremented, right? So we scroll down and we see it. We're actually using repeat here, right? We're using repeat, 5, it's going to start at 0, 0, 1, 2, 3, and every time it's going to call this function. And this function is going to push onto labels, which is an empty array, this, unit 1, unit 2, unit 3, right? Why are we adding +1? Does anyone have an idea?
So you start at 1 instead of 0.
Precisely. It's that simple to start at 1 instead of 0. People think 1 base. Computers think 0. Should. They usually do. Think 0 base. Right? So it's that simple then. All right, and then there's your result. Okay. Getting down here. So here's what we're doing. We're creating a new function here, greater than. Right? Greater than takes a value. And what does it return? Who wants to explain this one to me?
Boolean.
No? Someone, who wants to do it?
It's gonna be true or false.
Okay, we got the Mike, right? Okay. Mike, explain to me what this function does right here. Greater than is returning something, right? It's returning a function. We know that. We know it's returning a function because we see something. We call it the fat arrow, right? So we have a fat arrow. We know that there's a function there. It's that simple. What is that function doing?
Equal, greater
As long
than.
as it's less than 10, it's true.
Just read to me what this is doing.
Taking the function m.
Not the function m. Let's see. Anyone else want to give this a shot?
Yeah.
Robert in the back.
Given m, returning m is greater than
Okay. A little more specific. Given m, what is it going to return?
the Boolean value of whether or not that m is greater than n, which defines.
Precisely.
Ah.
Precisely. That's what he said. I'm going to repeat it.
He said
it's
function, right?
it's greater than is taking a value n, right? And it's returning a function. That function is taking a value m, right? So greater than is taking the value n, and it's returning a function. The function it's returning is taking a value m, right? And when that is called, the result is whether or not m is greater than n. So let's go through this mentally, and then we'll show you code, right? If I say greater than 5, n is 5, right? What is this function going to be? Robert, n is 5.
The function will be given m is m greater than 5.
Given m is m greater than 5. That's it. So now I have a function. Given m is m greater than 5. I'm going to pass into that function. Let's say I pass into that function
Oh, that's
7.
cool. The function fits right there without saying this is going to be a function because you use the arrow.
That's exactly right. The fat arrow function is smaller. You could
Yeah.
put the whole function syntax there and make it longer, but yes, that's right. So now we have 5 for n, and I'm providing 7 for m, right? And now I have 7 greater than 5, and that's going to evaluate in JavaScript to a Boolean value true, and it's that simple. So let's take a look, and I'll show you actually how that works. This is higher ordered functions. So we have this here. I'm gonna copy and paste it because typing 5 words is too much work. Okay? And here we go. Greater than. Now, greater than 5. What is that going to return?
Oh.
It's going to return a function.
Oh.
It's going to return a function. Right now, what is it going to look like when it returns a function? What is it going to say?
Function.
That's it. It's going to say function because Node can't tell you what a function does. It doesn't do that. It just simply says function. So if I hit enter here, we're going to see function, right? So we know what that function does, and we know what it's expecting. It's expecting one expression, right? How do you call a function? Parentheses. It's that simple. Greater than 5, I'm adding another set of parentheses, and I'm giving it something else. 3. Right? What is that going to return?
False.
False. Right? Now here's the catch. I'm showing you how to execute them both side by side. But the point of this lesson is to show you that you don't have to. This is an abstracted notion of the greater than operator. So if I say here, let's say greater than 5, we'll say let greater than 5 equals greater than 5, like that. Now, greater than 5 is going to show what when I hit enter here? Function, just making sure everyone's on the same page. Now if I call it greater than 5, 3, I'm going to get
Well,
false. For the same reason that it was false up here. You got it right the first time. So the thing here is that we're creating something, right? And that something is simply returning this notion. Am I greater than whatever you started with, right? Okay. Here's the example in the book. They're doing greater than 10. They say greater than 10 is essentially, they're creating this function, greater than 10. It's returning a function. That function is essentially the same right here. They could have written let greater than 10 equals 10, or here, m. 10 greater than m. That would have also worked, right? That would do the same thing. Does everyone see why that would do the same thing? Does anyone have any questions about why that would do the same thing? This function, greater than, is generating this down here. We give it a value, 10, and it, hold on, 10, it's backwards. There we go. That's what it actually should have been. Okay. These are the same now. Now we get it, right? I don't know if anyone was confused by that. These two things are the same because greater than is essentially a factory. It produces functions. You give it a value, it produces functions. That function is just simply comparing the value you give it with n. Here, we're creating it with 10. So this is what we're returning. Take an m and see if m is greater than 10. I could have just done it the less agile way. I could have just said take an m and see if m is greater than 10. Then I wouldn't have to call the function to generate it, right? You can do it either way. The difference is if you do it the top way, you can usually save some code. Because if I need to write greater than 5 here, right, I could either do this, or I could do this. So you can see which one of those, you say, okay, the first time, if these two are the same, why would you write this whole function just to do this? Why not just do it here? Granted. But when you start to do this multiple times, you can see why we use this functional paradigm. Because now I just write greater than 5 and I get it again. I don't have to write this. So if I write this once, I don't have to write this each time. And that's the whole concept we're trying to do. We're trying to reduce redundant code with this functional method. That's what we're doing. We're returning functions rather than having to write them ourselves. Okay. Anyone have any questions on this? I see a lot of faces that are like, I may not be so sure about it, but, and I know it's a lot to swallow, but if you got any questions, I'm happy to answer them. And we're going down a rabbit hole.
How dangerous is white spacing in this scenario? So like you've got like an extra white space between your m and your greater.
It doesn't matter.
It doesn't matter?
No. Okay. Any other questions about the functional stuff?
Same with indenting, right?
Yeah. JavaScript is very, very lax about white spaces. There are some places where it matters, but we're certainly not going to go into that here.
So using the arrow, it's kind of like making an unnamed factor then. So the function, I mean, so it doesn't have a name. That function have given m.
Precisely right. It's given a name right here because we're assigning it to greater than 5.
Yeah.
But the very notion of using the fat arrow is to create what you will often see called in other languages lambdas. That is a lambda. A lambda is an anonymous function. These are just terms. We're not going to get into them here. I don't even much care that the book gets into them because I think it's confusing for a lot of people. But that's right. It's an unnamed function or an anonymous function until you assign it to greater than 5. Right? So when we pass it here, when we return it here, we're returning a function. That's a function. It doesn't have a name. You can't call it like you could another function. We can call this function greater than 5 because we define it with a name. We're returning a function here. That function has no name. It's anonymous. It's unnamed. Right? We give it a name here, and we give it a name here. When we say greater than 5 equals greater than 5, we're giving this a name. But it doesn't have a name the way it sits there.
Is there an innate connection between the fact that it's returned and the fact that it's anonymous? That is, can you return named functions and can you call anonymous ones?
You
You
can
can't call
certainly-
anonymous ones, right?
You can call anonymous ones, yeah.
Oh.
So let me just show you that, right? What does it look like to call an anonymous function? Okay, how do you call a function in JavaScript? Really quick. Parentheses, right? Let me show you this. If I was to do this, x equals x plus 5, and then I was to say 6, what is that going to do? Anyone want to take a guess? 11. That's calling an anonymous function. That function has no name. You can call an anonymous function, to answer your question. Now, your earlier question, can you name the function you're returning in that section? No, you can't. Okay. Does everyone see this? Does anyone have any questions about the recursion? Did I just blow anyone's mind with this
You
thing?
blew my mind when you told me I didn't have to define variables with like braces. I didn't put brace my variables. Like when you said you're defining the function,
Okay.
you don't have to tell it to.
I'm going to recap on that point really quick. Okay, we can say this, let a equals, and then I can say function x, x plus 1. That's one way I can do this, right? Return x plus 1. Whatever I give it, I'm going to get a value 1 higher. That's one way I can do it. Then I can say a5, right? Now, we just saw another way. I can say let b equals, and then I can say x, x plus 1, right? Now, if I say b5, I get the same thing.
That's
This is a different syntax to do the same thing. Now, and by the way, I had, oh, there we go. Now it's pretty. Okay. We went over this in, I think, the first class, and I said that there's a very slight difference between the two, but we're not going to go over it. The book also says there's a slight difference between the two, and the book doesn't go over it. So just follow with me on this. These are two syntaxes. They do the same thing. And as a third point, we have this function c x. This is essentially, I could have assigned c either way. So now if I say c5, I get 6. So we have the method up here at the top, let a equals, and then we give it a function, right? We have the fat arrow method, let b equals, take an x, return x plus 1. And then we have this method down here, where you explicitly give it a name, function c, x, return x plus 1. This is creating a function as a, this is creating a function as b, this is creating a function named c. All do similar things. They're all very close. That's the recap on it. Anyone else have any other questions on that? Syntax, functions? Yes.
After you define C, can you do like B equals C, and then B is now pointing, but is now C?
Yes, you can do that for any of those. Yeah. Yeah. Okay. because JavaScript under the hood, even though this wouldn't be the same in C, is actually doing just that. Okay, anyone else questions? Okay, let's move on.
Thank you.
No problem. Okay, so now what we're seeing here, this is actually a good example. So most of the examples in the book I have a lot of criticisms about. This is a pretty clever one. So we have this function we're creating called noisy, right? Anyone have any idea about what noisy does or want to give a shot at explaining noisy? My man in the middle. Why are you so quiet today? Hey!
I'll give it a try. Okay, so we define a function called noisy. It accepts one argument f, then it returns another argument with an unknown amount of arguments. And in there, it prints out calling with and then whatever those arguments are. Then it defines a new variable, result, which takes the original argument that you gave noisy. Oh, now I'm getting confused. Okay, oh, I get it. Okay, I'm still with it. Okay, so, okay, so basically it's setting result to be that the new return function, maybe? No, it's losing me.
You are so close.
So close?
You are so close.
Okay.
You're killing it. Does anyone else want to give it a shot? Let's give it a shot. And it's Medi? Okay.
Defining a function named noisy, it takes in a parameter, which is a function, a loaded function with an indefinite number of arguments, and it prints to the console calling with, and then prints the arguments. and it defines another variable called result, which is whatever the return value of the f function that you're passing in is with all the arguments, as many arguments as you'd like to pass into it, basically. And then prints called with, prints the arguments, and then returns, and then prints the result, and then returns the result.
I could have done better. That's exactly it. That's exactly it. You nailed it on the head. Every word of that was precise and accurate. That's precisely and definitely what's happening. Okay, line 101. So this is kind of cool because what they're showing you is essentially when you call a function, you don't know what arguments that function's given. The function may know, but you don't have a method of logging it. So if you want a method of logging what arguments you're providing to the function and still calling that function, Noisy's doing that. Noisy could have probably better been called call function with output, right? Because normally you don't see the arguments you're passing to the function, output it on the screen. You come back here, right? I called B5 and it said 6. You guys see this? 6, B5, 6. It's not actually telling me anywhere that you called the function B with the value 5. It's not telling us that. Noisy is providing you a method to wrap B and tell you that, right? So if you want to know that kind of stuff, you want to know what the arguments are that are being provided to the function, you can wrap that function with something like Noisy. Noisy will output those arguments, it'll call it, and then you'll be done. In this case, it'll actually tell you again. Okay, so I want to show you here how this works because it's kind of cool. This is Noisy. Noisy gets put here. Now, Noisy is essentially going to wrap whatever function you're giving it, right? That's cool. I just want to be clear about it. This construct here, ..ars, we didn't cover this all that much when I went through it. The book covered it a lot more, right? And the reason why I didn't cover it is because you don't often see this, right? Does anyone know what that does? Did anyone remember or read that part of the book?
Where it's like it takes everything before, like.
That's exactly right, 100%. But does anyone remember what it was called for the bonus question?
Rest.
Yes, right operator.
The rest operator.
Rest operator. Check, is he cheating? Did he cheat?
No, I actually remember that one because you said it.
Okay.
It was like
I used to work with him for like 10 years, so I had to answer. Okay.
I remember that because it was the rest of the stuff.
That's right. It's called the rest operator. So yes, you'll find it in the book. It's doing precisely what it was explained. It's essentially saying, whatever I receive, throw into an array, call the array args. That's what the operator does. So if that was confusing anyone, hopefully that's a little clearer. This function essentially says, I'm taking Noisy's taking a function as an argument. That function's called f. It's wrapping it. It's eventually going to call f, right? It's going to call f. But before it calls f, it's going to do this. And after it calls f, it's going to do this. And that's the catch here. Noisy should have been called wrap with output or wrap with log. Because that's what it's doing. It's wrapping the function you give it with extra output. Okay. So we have Noisy. We're going to create it. We're going to say we have this function C. C just simply gives me back the output. I'm going to say let Noisy C equals C. It equals rather Noisy C like that, right? And I'm going to say Noisy C 5. And there you go. Calling with 5. Called with 5 returns 6. 6 is the return value. Noisy C is wrapping C with this function Noisy. And it's doing and by the way, we had this question earlier on. If this allows you to write shorter code that's less redundant, why doesn't everyone use it? And if you all just look at each other's faces right now, I'd say the amount of people that understand this, probably 10, 20%, you're going to look at this for quite a while before you actually clicks and this is natural to you. So this is the reason why every programmer doesn't use this method, is that it's somewhat a little difficult to wrap your head around. You're not alone. Calling, we provided the value 5, calling with 5, called with 5, return 6. All of that's coming here, right? We're giving it a function, F is getting set, right? F is being set with C, right? C is very simple. It takes a number and returns the incremented version. That's what's here. Now what we're doing is we're returning a function, right? So when you call noisy, you know you're going to get a function. We're calling noisy here. We're calling noisy because we have parentheses on noisy. We know we're going to get a function back. We're calling that function noisy C, right? So we're returning a function. That function takes any of the arguments it gets. It doesn't care about them. It doesn't know what they are. It puts them all into an array. And then it says console.log, calling with arguments R. It's going to say, these are the arguments I got. And then it's going to call F, which is what it wrapped, with those arguments, put out some more things, which is the result. Right? So before, when we called C equals 5, it returned 6. Now that's coming down here. That's going to be the result. The result is when you call the function with the arguments. So it's going to print out the arguments, print them out again. This whole part is the same. The only difference is you're adding in result. Return result. And then you return it. And that's it. I unfortunately don't know that many other ways to explain it. I'm going to walk through it. Does anyone have any questions on that? Can anyone, by the way, asking a question is a tremendous skill. If you can ask a question about this, please do. It's not always easy.
Something you would use in debugging, correct?
You could definitely
Like
use this to
rip the code
debug a
apart.
function. That's right.
Start dumping out information.
If you were using C in your programming code, right? Like let's say I have this function here, I have this, and it's calling C6 plus C5 plus, C7, something like that. You have something like that that's kind of cryptic and you see it a lot in your programming code. You get the result back, it's 21. You want to know later what all the arguments are and how they all look, you can do that, right? You can actually call noisy and replace it. So you could say here, let D equals noisy C, and you could go back up and just replace them with D's. Now you know the result is going to be the same. The only difference is you're going to have output, and you can see it. So yes, you could definitely use this to debug. Debug means you're trying to figure out what code is doing and where bugs are at. And this provides you a good, it's useful to do it. Now, the Chrome Debug Console, which we'll get into in a much later lesson, does a lot of stuff for you. So you probably wouldn't want to write this one. But yes, you could use this to debug. Any other questions? Yes?
How do you get 6 from C5?
How do we add?
The function adds up.
The function is adding,
that plus 1.
so it's adding 7 plus 6 plus 8 right here. It's adding the return values.
No,
Right.
but C5. It's on C5.
This one here?
The
Up
first-
higher?
C5, yeah.
I just want to,
The first one.
oh, this one here.
Yeah.
Okay. How did this, where is this getting defined?
Yeah.
So this is defined, we define that here. Function C takes in X, returns X plus 1. If I hold my middle button, I can scroll up, and you should see it right there. Right? So this is where we actually define C. And we showed 3 different functions. I showed A, and I showed B, and I showed C. And I showed 3 different syntaxes to declare a function that all do the same thing. So when I was using one, I just chose C as an example, just to build off of those earlier things. Did that answer it?
Yes.
Great. Anyone else? Questions? Comments?
I have a general question.
Definitely.
Is it, I just asked one. Is writing programs this way, this functional way, given the hit that you take in maybe readability up front for someone who doesn't think this way, is it worth it to think through and write a program this way as opposed to maybe just return a value, spit out or whatever? That question makes sense?
Yeah, it does.
Because they are kind of hard to crunch through, like what you're saying, returning a function, what does the function do? But like, is it worth you say that's the way programs?
Here's the thing about this. The thing about this is that this is only complex because you probably haven't seen anything like this. There's no real world analog to something like this. It's just something you're going to have to learn. If I look at someone like Ed and I say, Ed, what is this doing? Ed's going to know right away what it's doing. He knows it really, really well because he's seen it a lot. Right? This is a special construct in computer programming. After you see and understand this, I guarantee you the confusion will go away. It's not going to be something that's going to be very easy to teach in a 1-hour class or even in a 3-hour class. This is higher ordered programming. It's literally a whole branch of programming shrunk down into one lesson. You know?
But Evan, if they're well-named functions, to me it simplifies things.
For me, it simplifies things too, but that's because I understand the constructs. Not everyone will,
Yeah.
and they're gonna have to get acclimated to it. Is there a cost, and some people simply can't wrap their head around it? Yes. You know, Lisp did it in the '60s. It's not the biggest language in the world, partly because it's harder to understand this stuff for many people.
Didn't you have to have a special key for this?
No, we're not going into that. All right. Anyone else? Any questions? All right, cool. Let's go through it and break it down. Okay, so now we're providing new functions that provide new types of flow control. This is cool. We already said we can implement loops with functions, right? We can also implement conditionals with functions. How do we do that? We do that just like this. This is a method of implementing unless with a function. You can also implement an if with a function, right? So some languages, by the way, have unless, which is also something we're not going to go into, but I know someone's going to make the comment, so I'll beat them to it because it's fun. Unless is taking something called a test, right? The test is an expression, right? You know it's an expression because you call functions with what?
Parentheses.
Parentheses. Does test have parentheses?
Yes.
No, right?
Oh.
If test was a function, you would see parentheses right here. I almost thought I didn't see it right. Yeah, test doesn't have parentheses, so you know test is not a function call. Test is an expression. That's a Boolean, right? So you're giving it a Boolean, and then you have this thing here called then. Now, what does then have, Jason?
Parentheses.
He's right 50% of the time now. Parentheses. That makes then a what?
Function.
A function. Now we're calling a function then. You can call it whatever you want. Point is, you see parentheses, you know it's a function. You know that function is there and it's meeting up here with then. That's just the name of the function. So we're taking an expression in this, which is Boolean, and if that expression is not true, we're calling that function, right? Now, that's cool. I would have shown this first because it certainly would have made more sense. Okay. This would make more sense to me, right? And if you haven't seen that, then it's a little harder to come to this. This is one of my problems with the book. Let's go through this one. This is taking test. Does test have parentheses, Jason?
No.
Now he's right 2/3 of the time. Looking good for him. Okay, we have this function then. We're saying if this is true, call then. Right? That's a simple if construct in a functional programming language. Now we come up here unless. We're saying if it's not true, call then. Simply inversion. Right? So they're showing you how you can write these things in a functional language. Now, we have this thing called repeat. We've seen this guy before. Repeat's taking this number 3, and it's essentially going to start at 0 and increment until it hits 3. 0, 1, 2, done. Now, we're saying for each one of these, it's going to execute this function right here. Right? Now, for those that are looking, I'm highlighting all this stuff because this is the function, right? So repeat for each different one of those. It's gonna call that function. That function takes an n, and it says unless the variable you give me modulus 2 equals 1, call this, right? So we saw this earlier on. We saw this, I think, in lesson number 1, right? We saw this modulus 2 thing. What does this do? Does anyone want to give us a description, a summary of what this does?
You do the remainder after you divide by that number.
That's it. It's the remainder after you divide by that number. So if I give you a number, let's say I give you a number 3 modulus 2, what am I going to get back?
1.
If I give you 2 modulus 2, what am I going to get back?
0.
If I give you 1 modulus 2, what am I going to get back?
1.
1 in this case. That's right. 1. So it's very simple. what we're going to do here is we're going to call it with 3, 2, and 1. I'd rather 0, 1, and 2. 0, 1, and 2. So we have unless 0 modulus 2 equals 1, right? Now, what is this going to evaluate to? 0 modulus 2 is what?
0.
0. So unless 0 equals 1, right? Now what is 0 equals 1 evaluate to?
False.
Okay, unless false, right? Unless false, run this. Now here's the deal. Unless is going to run this, right? So it's going to run, and the very first thing this outputs is 0 is even. Now we're going to look at that again. I'm going to run through it one more time. Repeat 3. First thing it's going to get called on is 0. 0 modulus 2 is going to be equal 0. 0, if I just replace this right here, 0 equals 1 is going to be false. I'm showing you this is what it looks like the first time we run this. Unless false is going to run this function, right? So if anytime you see unless false, this function gets run. Anytime you see unless true, this function, the function you give it doesn't get run. Do we get that? Okay, that's key. Now this is the first time we've seen this. This is actually, repeat is taking a function, which is in and of itself calling something that is requiring a function, right? So we have this, you see also, let me show you this too. Look at the tabs. This is the first function. This is inside of the second function. Remember how I said tabs designate scope? Right? Coming back to that idea, we're seeing that again here. Because anything we declare here, where this console log is, this is only scoped for this fat arrow. Right? But we have another fat arrow here, and that has its own scope. I'm just trying to tie it all together for you. So, yes?
And so you're not passing anything into the second function? That's reading from the global scope?
That's exactly right. That's exactly right. The second function, this, let me give you another easy one. Jason, what's inside of the parentheses?
Nothing.
Nothing, right?
No arguments.
No arguments. And the reason why is if it's not taking any arguments, then you know if it's going to print anything out, that n there has got to come from above. It's got to come from the scope outside. And that's what we're seeing. N is provided to repeat. It's not provided to unless. Now, could it be? What if I do right that? So if I did it like this, you're defining a function that requires an n, but we're still not passing it the n, right? So this is a little tricky. That's why they're doing this. I'm showing you that in this case, you're right. It's reading from the global. It's doing that because you're not giving it arguments. You know, it's defined as not taking any arguments. It's reading from that global scope. Okay, we had one person who picked you. By the way, do you feel comfortable with this? Because
For the most part.
For the most part.
If I put an n in there, it wouldn't work?
If you put an n in there, then the function is expecting an argument. But how are we going to send it an argument? Unless doesn't have the ability. See when we come up here? Unless is calling then. What's inside of these parentheses? Not you, Jason. You got it right last time.
Nothing.
Nothing. So if there's nothing inside of these parentheses, we're not passing anything to that function. So if you put the n here, right, it's going to be undefined because you're not calling it this time. If I was to say up here, right, to give it a value, like if I was to do then it would, right? Now I know a lot of people aren't getting that. A lot of people are missing it. I'm just trying to keep hitting on this thing on different angles so it clicks. And really, this is a huge part of this is going to be exposure time. You know. Okay. Let me see here. Okay, I'm making it revert back. Yes, let's take some questions.
Okay, so if n is defined globally, could you actually just write for that n equal whatever, or would it actually go all the way back outside of the repeat function to find n?
No. And the reason for that is, because n is being defined right here. That's where n is coming from.
You can't
So-
do it 2 times. The suggestion is that you define it globally as let some people in, and then you're doing it a second time and then repeat. Is that what you're proposing?
Well, it's just as you said that it, within the scope, the n had to go back out globally. So like when you initially define n within repeat, does that actually define it globally, or is it just within the scope of repeat?
Just within the scope of
Yeah. It's global here.
It's actually just within this little callback right here, right?
But could you have also defined it literally globally, by just saying,
How would I?
n equals 7?
Here's the thing. The thing is, you want n to change. Repeat is changing n, but repeat is changing its internal copy of n. It's sharing that internal copy of n. You see, so it's setting here n equals 0, n equals 1, n equals 2, right? It's setting that because it's counting up to 3. That's its own internal copy of n. Then what it's doing is it's giving that copy of n to this callback, to this argument right here. It's sharing with you its internal counter. Right? If you had a global thing, it would work fine, but something's going to have to increment it.
Right.
So n
But it would have to
could,
be a counter.
right?
global thing.
N could increment a global counter, and everything can reach from that global. That's not very good programming design, because you
Right.
want to keep this stuff compartmentalized. But yes, you could do that. Yes.
That's because of the closure? Is that
That's
where
right.
the closures come in? Will that help through the closure?
That's exactly
example?
right.
'Cause
Yes.
that's throwing the function, it's keeping it in memory. Would help to show that.
We're allowing something else to get access to that n. In this case, we're allowing this function here that I've got highlighted.
Because it's the outer.
That's right.
Compared
It
to
has,
our last one.
it has access to repeats copy of n. Yes. Okay. So yes, it's closing over n. Anyone else? Any questions?
How does the function like iterating? Is there for loops or something?
How is the repeat function iterating?
Yeah, like n increasing.
Okay, let's go back. Let's. It's hard to show all these things at the same time. Let me take this here and let's go here. Let's paste it. Let's repeat. Remember this? So this is where we're doing it, right? So we have a function repeat. Repeat takes an n, and it's counting up, starting at 0, 0, 1, 2, and it's calling action every time. Coming over here and giving it a 3. So we know what it's going to do. It's essentially going to say, let I equal 0, I is less than 3, I plus plus. And then it's going to call action with I each time. We're going to call here, we're going to call this callback, this guy right here, we're going to call that with the value, right, of n. So as we go through this, and as we increment n and repeat, we're going to call action with it. That's what we're seeing. Hope that answered it. Did it? I know this is a lot. If you have a question you can ask it, because like I said, it's okay. So let's go through here. Script data set. Great. Horrible examples. Okay. So here's what we got. I'm trying to think about how much of this I want to explain to you because you did a horrible job. You have different things inside of a computer called encodings, right? The one that we're going to go through today is essentially the Unicode encoding. Inside of Unicode, you have different languages. The great thing about Unicode is that no one has to worry about any other type of encoding. All of the languages in the world fit into the Unicode code set, right? So every different character from every different language has a number, right? So you look at A, the number for A is 41. If anyone knew that, there's your trivia point for the day. All of your different characters for every language in the world have a number, right? And all of the punctuation marks, all of that stuff. The diacritics, what they're showing you here is the name of the language is called Coptic, and it represents the numbers between 994 and 1008. And it also represents the numbers between 11,392 and this, and also in between this and this. Right, so there's a language called Coptic, whatever. I don't think it's actually a language, but yes.
Yeah, really.
Well, I think it's a writing set or whatever. Anyway, different thing. So there's this the set of characters called Coptic, and it represents all of these 3 different ranges. And inside of it, the Coptic characters are supposed to be rendered left to right. Right? Some characters are right to left, like Hebrew and Arabic. Coptic is left to right. The year is -200, and no idea what they're doing with that. We'll see it later. Living is false, and then they're giving you a Wikipedia link where you can go waste your day. Okay, so that's how this data set is represented. We asked this question earlier on. The question was, how do we build a program? And I said, we start off by getting everything into the computer. This is how they're doing it. They started off by getting what they need into the computer, and this is the information on Coptic, right? Okay. So now scrolling down, we're creating something here called filter, right? Now let's go through with what filter does. Filter takes 2 things. It's going to take an array, and it's going to take a function, right? So what it's going to do is it's going to create an empty array internally, and then it's going to iterate through all of the different elements of the array that you pass it. And it's going to say, if the result of that function with that element is true, add it to this array. Add it to the empty array, pass, and then return it. So this is really kind of cool, right? If you create a function that does this, and I say, my function is, check that x is greater than 10. I just did that, right? Then what I can do is give it a bunch of numbers and filter for all numbers greater than 10. Then later, if I want to create a new function less than 5, I can give it a different set of numbers and this new function less than 5, and it'll filter out all the numbers that are less than 5. This is a higher ordered function because it takes this thing called test, which is a predicate, and it says, I'm going to apply that predicate for every element in this array. And any of them that return true, I'm going to add that to a new array and return that. So let's take it. We're going to copy this over, filter, boom. Now we have it in here, right? Let's say I do this, filter, 1, 2, 3, 4, 5, 50, right? And then I say x is greater than 10. What is this going to return? An array with 50. If I say x modulus 2 equals 0, what is that going to return? It's going to return all the even numbers, right? 2, 4, and 50. We created something, a higher order function, filter, which takes a predicate. That predicate can be whatever I want. And it's going to iterate over every different element of that array and say, did that predicate return true? If it did, add it to the output list. But it doesn't know what that predicate is, and that's the beauty of it. The very fact that you're filtering by a certain criteria is removed from the very fact that you're filtering. You've compartmentalized those concerns. So we can use the same filter function on both greater than 10 and the even test. Okay, but alas,
does it matter which order you put those words array and test in the parentheses?
Yes, it does, because the filter in the first argument, it's defined to take the array, and the second argument is defined to take the test.
Okay.
Now, if I switched it here, can I also switch it in the call? Perfectly fine.
Okay.
Yes.
That's okay.
Okay. Let's go up, and I want to find the whole list of this horrible data set he's got. Here we go, intro.js. Remember, all of the code for the book is available online on this slow website.
Capital A is actually 65, not 41. 41 is hex.
Ah, okay, yes.
Fun fact.
There we go.
Moving on.
Correction. We'll do ASCII bit character patterns in a minute. That'll be a lot of fun. Okay, look, here. We're pasting all this stuff in here because that's a really great idea, by the way. Paste random code into it. Okay, So now we have created this whole thing with the scripts. Remember, we went through this in the last crappy example he gave you that I didn't like, that I argued against. There was that little snippet of the log that he had in the book, and I said, when we're doing this in class, we're going to use the actual data set he provides in the code, and then that's exactly what we're doing again. He's providing to you this data set right here. Yeah, wherever that would be there. He's providing you this little snippet, but in reality, it's really all of this crap here in scripts, right? So this is all of it here. So there's a lot of stuff in this little data set. Okay. So I copy and paste the scripts into it, and now we can see he's got this filter, and essentially we've already went through what filter does. He has a filter, and it's going to filter over the array scripts, right, which is all of this stuff he's got right here. And what it's going to do is look for this thing called script.living. Now, what I assume this is, because this is pretty well documented, are people currently using this language set, right? So there's, I don't even know the name of it. It's not verbal language. It's like written language, right? This character set. Are people using these written character sets? So there's a flag in here called living, and a lot of these have false on them. Some of them have true, right? And essentially what you're doing is you're saying, this is my data set of all the different languages. I want just the ones that are true. Filter is doing that. So we're giving filter the scripts with all of that stuff in there, and we're saying, find me just the ones that are true, right? So here's the gig. It's going to go through each one of these guys here, like ye, and it's going to say, for each script, return script.living. Script.living is just true, right? JavaScript has Booleans, true and false. If you have those Booleans set, or you have something that evaluates the true, like 1, right, then that's going to work. So it's simply saying, put that here, right, script.living. So when it gets to ye, it's just going to replace it with true. True satisfies filter. That's what it wants. So because it's satisfied, it's going to add that to the output array. And that's it. Does everyone get that? Does everyone get what that's doing? Even if you don't get the total, thing about. Okay. So, moving on. Okay, so here's the kicker here, and I think he says it somewhere here. There you go. Like for each, filter is a standard array method. This is the most important sentence that we've probably read so far. A lot of these functional things that we've gone through. Remember how I said JavaScript has little parts of it. It's a multi-paradigm language. Filter is very popular. Every language has filter, or some form of it, right? This is in JavaScript. You don't have to write it. So if you don't have to write it, and it's already in JavaScript, and it already works on an array, then how do you use it? You do it like this, right? We had this before. Let's go back to our other example. Okay, you can't get back to our other example. No, yeah. Seriously. Let's do that again. Node let a equals 1, 2, 3, 4, 5, 50. That sounds good, right? And then we said here, filter, and we're going to filter that list. How do we use the one that is in the standard array method? Anyone want to take a crack at it? How do we call a standard array method?
Mash on tab.
Okay, that's a good point. That's always a good point. That's always right in this class. You mash on tab. That's a great way to find it, right? So you can say a dot filter. We had a lot of people shout that out. That works fine. A dot fill. Okay, you should never type the whole filter because you can always, Jason?
Tab.
Tab, right? So you just like that, right? And you get it. There's an a dot fill and an a dot filter. If you forget them, look at them all, but you'll get there. So a dot filter, and now I can say let's get all of the a's that are greater than 3. Of course, I need the fat arrow. 5, 6, and 50. That's how you call the standard method, right? So in the book, he defines his own, which is a really good practice, and he shows this is how it looks like when it's implemented. It's a higher ordered function. There's a standard array method, and you can simply call it by using array.filter. Okay, Does everyone get both the fact that there's an array.filter there, that you call it by using array.filter, that if you forget it, you can use array.mash on tab, and that tab completion will fill it out the rest of you?
Yes.
Okay, cool. There's another one that we're going to do here, and this is also very important. This is called map. Here's the kicker, guys. Filter, it simply removes elements from the list it's going to return, or it adds elements to a list in which it will return, however you want to think about it, right? The internal implementation of filter is it adds elements that satisfy the predicate, that satisfy that function, right?
Like while.
The predicate is like while, yeah. It's just, it's returning something, whereas while is doing something. Okay, mapping though is slightly different. Mapping is going to take a list of elements, right? And it's going to change them in some way, shape, or form, right? So if you have a map, you're always going to have the same amount of elements, right? You're just going to return different things, right? So look here, let me give you an example. Actually, let's use his example, and then we'll see if it's good enough. He's creating a function, map, and it's going to take an array and a transform, right? So that array, he's starting off the return value with an empty array, and he's saying, for each element in the array we pass in, I want to push on the transformed element. You give it a transform, you give it an array, and then it simply loops over the array, right? And it creates a new array with each element transformed. Okay, so here's an example. He has this, let's copy this into the code that we have. Now we have a map, and he's calling, he's going to call, okay, so the first thing he's doing, this is kind of cool, let's do this here too, I like this. We looked before where he was filtering to get the living languages. Do we all remember that? We just did it. Now what we're going to do is we're going to filter them all for their direction is RTL. We have left to right scripts and right to left scripts. Arabic and Hebrew are the right to left scripts. He's going to look for the languages that are RTL, and he's going to save all of those languages in a new array called RTL scripts. It's not going to touch the old array. This is filter. Filter doesn't modify anything it's running on. You're going to get a new array called RTL scripts. Let's see what he's got in there. He's got a lot of stuff. Because there's a lot of dead languages that also are written it this way. Lydian, there you go. So he's created a new array from this data set with all of the right to left languages. And now what he's going to do is he wants to get out of all of them the language name. So if you look here, there's a name Samaritan. That's a right to left language. He doesn't want the rest of this crap. You see how you have all this crap here? Ranges, direction, year, living, and link. That's all extra data. He doesn't want all of that. All he wants is an array of the names. How does he do that? He uses map to get it. And he uses map because he's saying for each different element, I just want you to take the name. So this is, before he does it, this is an object, right? We went through that last class. We went through how an object in JavaScript is like a hash, or like an associative array, or a dictionary if you come from a different background. An object in JavaScript matches your keys to your values, right? So this here that I'm highlighting in blue, this is an object, right? And he only wants to get the name value of it. Bofu Mufu. Well, not actually this one, because this is left to right, but on an RTL one. That's what he wants. He just wants the name. So we're going to take it, and we're going to take this array of objects, and we're going to map it to an array of strings. And say, just get me the name. Just get me the name. Just get me the name. And that's how we're doing it. So we filter first for the right to left languages, and then we just get the names of them by mapping it through. So that's what he's showing you. Now what we have here is we have a filter and a map together. And here's the thing, again, I told you the most popular functions are already in JavaScript. Map is also already in JavaScript. We call filter by doing what? How do we call filter, the standard version? Dot filter. How do we call the standard dot map? I just cheated, dot map. There you go. So you call the standard map by calling dot map. So you don't actually have to define this and pass it in. See how he takes his, and he's saying here, map, this is his custom map. He's providing it the array, and he's providing it the predicate. See how we did that too with his filter originally? When we first created filter, we provided the array and we provided this function. The standard version that you call on the array. So you don't have to provide it. You just call it with that function, right? So this map function down here, he's calling it. You can call it anyway. Like, okay, he doesn't actually say it, he just talks about it. So he says right here, the map method transforms an array. Like for each and filter, map is a standard array method. He doesn't actually show it. So what we would do here is we would say this, right? We could say scripts dot filter dot map. Right? So I'm showing you is how that looks. Filter is going to look for all of the ones that have the s.direction direction set to RTL, and then if we don't map over it, we're going to get the whole object with all that stuff in there, including the living flag, the ranges, all of that kind of stuff. We're going to map over that and pull out just object.name. Okay, any questions? So now we're chaining maps, we're chaining filters, we've shown you both of them, predicates, and these things called transformers. Okay, we have one more to do, and that's it, because we're not going to do composability, I don't think. Does everyone feel comfortable with this pace? I don't really I need to know how many people are actually grokking this, because if I'm missing you on this, then we gotta either go back and cover it and split the class up, or and by split it up I mean do another half of this on higher order programming. Or
the filter part, the map part, just everything so far today.
Higher order functions, filter, map. How many people are feeling comfortable with it? Because I'm seeing I'm losing a lot of people, and it's not going to be a mess.
I like the pacing, but if I had read the chapter in advance, I would have been less lost. I don't feel like the pacing's the problem though. I need a little more exposure to wrap my head around it.
It's going to require a lot of exposure, that's the problem. And if you don't read the chapters, I'm happy to help out in the class, but it's going to be, it's going to be a much less good,
yeah, I understand.
The investment will pay off.
Sure.
I'm glad I reviewed this ahead of time, because it took me probably a good half hour, not a half hour, but probably a good 10 minutes to spend on each of these steps to understand what was going on. Because it wasn't, these higher order functions were definitely difficult for me to understand. It's almost individual.
What if we were to do the exercises in another section? In other words, instead of doing what we're doing, which is very productive, but maybe needs some of us hanging like me. What if we did the exercises that he provides?
I think it will take a long time, huh?
It would be a whole nother, it would take twice as long.
Yeah.
Right?
I don't understand what he's saying.
Yeah, because I'm actually running every line of code that he's got in there. So when you say the exercises, you mean like,
at the end.
we're not even close to it. I'm not sure we're going to make that at all. If we want to do the exercises, we could do that. I can explain them in another class. But I don't think we're even get to that today.
Mm-hmm.
I'm just trying to what I'm trying to understand is how were we all feeling with pacing on this? Because
Well, instead of going from chapter to chapter to chapter, what if we did chapter exercises, chapter exercises, chapter? I'm just asking. I'm not sure.
I don't know either.
We never got the exercises on the last chapter, that's what he's saying. We went through the chapter, we never got through the exercises on the last chapter.
Okay.
Well, I think the point is, and if I remember correctly from last week, is that we go through the lesson so that the exercises are kind of remaining for us to do over the week and try to figure it out on our own, and we can come to you and actually have something with it.
My big thing about doing the exercises is that I think you can do that. I think it's value added too. But if I was to ask for a show of hands of how many people actually read the material, and I don't mean did the homework, I mean just read the material, my assumption is that it's around 20%. So if that number was closer to 90%, I think it would be very productive to actually go through the exercises. But if that number stays around 20%, then it's me just simply doing ad hoc examples, and you may as well, continue with the book.
Yeah.
But yes, if people want to do exercises, I have no objection to allocating more time to it. I think we're going to go through here. Reduce is getting very complex. So my big thing here is that if I hit on this, and you guys aren't getting map and filter, you're not going to get reduce. I'm just straight up telling you. And here's the thing about it too, for the people that are getting scared by this, most JavaScript programmers don't know reduce, right? So if I was to ask, Jason actually does quite a bit of JavaScript work. I know that because I work with him and I've seen him do it. Have you ever seen reduce used by anyone, ever?
I've never used reduce. I
Never
don't think I've
used
ever
it,
even
ever
seen it.
So maybe just covering it on like the conceptual level as opposed to like an actual use.
Well, I like both.
So you won't get too deep, but it's okay. I mean,
Reduce was one that I was
Because like MapReduce is used in a lot of technologies.
It is.
Yeah.
Besides just JavaScript.
Yeah, this is a super important concept. I'm not taking anything away from the concept. I'm just saying at the level JavaScript programmers work, they tend not to know it, which is unfortunate, and not to use it because they leave it up to the library. But it is super, super useful.
So let's do reduce, since you see
Yeah.
the value in it, even though it's less common with almost JavaScript.
Okay. First, I'm going to try to talk you through it just a little bit because it's going to be like, I hope it lessens the cliff that we're going to go up, because I'm not sure we have everyone to go up it anyway. Okay, here's the deal. The deal is filter in the abstract is taking a predicate, searching through all of the different array elements and saying, if you've satisfied the predicate, I'm going to add that to the output, right? So filter can only ever make a list smaller. Right? That's what it's doing. It's looking for it and it's filtering things out. Map is transforming a list by transforming every element of that list, right? You provided a transformer and it calls it on every element. There's another function.
How is that different from filtering?
That's not my mind, that was it. Okay.
It doesn't do filtering, it basically does, it does a transformation for everything in a list. It doesn't change the elements in the list, is that correct? The map.
Neither one of these two things will mutate the list. They return new lists, right? So they're returning new lists. Filter, if I give you a list of 10 elements and I say filter all of them that are greater than 5, you're going to get a list with 5 elements, 6, 7, 8, 9, 10, right? If I say I want to map that list, and I want to map it by incrementing every element by 1, you're going to get a new list that's going to have 2 to 11. Right? So mapping is mutating the list, and you're never going to reduce elements. You're always going to get a one-to-one mapping of input elements to output elements. Right. It's never filtering elements. You're always going to get a one-to-one output of input elements to output elements, and they're always going to be transformed. Filter is simply looking for specific things. Right? So you're looking for things by selecting. Yes. There you go.
Yep.
Filter, select, grep, all of these things mean the same thing. Different languages call it different things. Okay, so now the concept of reduce, right? Reduce, you're taking a list and you're trying to say, I have a list of stuff, they only want one thing, right? So how do you do it? For reduce, you give it a starting value and you give it an operation for 2 elements, and it simply calls them as it goes through that whole list. And it says, okay, I'm going to call this function with the first element of the list and the second element of the list, and then I'm going to save that, and I'm going to call that with the third element, and I'm going to save that, and I'm going to call that with the fourth element, save that, and so on and so forth.
Aggregate.
Aggregate, that's exactly right. That's a word that means something to, usually people don't understand the word aggregate, but yes, that's exactly the right word for it. Reduce is aggregating all of these values. And then the end result of a reduction is one value, right? So now that one value could be anything, but you're reducing it to one thing. So if we look here,
A good example would be, let's say, the mean of all the numbers in an array is an example of
exactly, or the sum.
some, yeah.
Sum is the one that you'll always see done. So let's go through it. Reduce is defined like this, right? We take an array, we take a function called combine, and we take a start. And what it's going to do is say, we're going to start off with that third element, the third argument we get to reduce. We're going to iterate through every element of that array, and we're going to call combine on the current element and the next element, right? So current is equal to start on the first iteration. And then we set current equal to the result of the combine function with both the current element and the next element. And then the result is stored in. So remember, let's go back to the example. We have 5 elements, 0 through 4. I take the 0 element, I'm going to set it right here to the current element, right? Now what I'm going to do is for every element in the array, I'm going to process combine the current element and then the element I'm on, right? So combine is 0 in the first iteration. I'm going to process it on 0 and 0. That's going to be the first time I run combine. Then 0 plus 0 is 0 if I'm summing. The next one is going to be 0 plus 1. That's 1. Then I'm going to do 1 plus 2. That's 3. Then I'm going to do 3 plus 4. That's 7. And each time I do that, I'm changing this current value, this aggregate value, and then I return that at the end. So that's what a reduction does. The reduction operates over the list and it reduces it to one thing. It aggregates that whole list into one value. So we can look here at the result that they're giving us, right? They're reducing the array 1, 2, 3, and 4 by summing it up, right? So this is the combine function right here, a and b, a plus b. So the first time you call it, it's going to look like this. Reduce 1, 2, 3, 4. And then we're going to say this is the sum. And then the second time you call it, you're going to get reduce 2, 3, 4. Zero, 1 plus 2 is 3, 3, 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, and 10. So that's what it's going to look like, right? All of these are the same thing, right? The 0 is the starting value when we run it the first time. The second time we run it, essentially it's the same as if we incremented the starting value and removed an element, right? Now what we're going to do is, I'm showing you each time we're doing this, we have this thing up here called current, and it equals start, and we're modifying it. We're passing in start, right? So start and current get set to be the same thing on the first iteration, right? Essentially, what you're passing as start becomes what you're returning, right? You set current to start, and at the end you're returning current. So these two things are intricately related. Right? They're intricately related.
It means you can aggregate less than all of the array, right? You can start anywhere you want in the array, like on the 6th item.
You could do that, but you would. Let me show you that later, because that's. I don't want to get into that right now. But yes, you could. You can do all of that type of stuff. What I'm trying to show is that the array here, we start off at 0, right? We set current equal to start, and we're returning current. what we're doing is for each element of that array, we're changing the value of current, the internal value of current. And what I'm trying to show is that internal value of current, we don't see that with reduce. But you could imagine it, right? You can imagine it because you know it's getting set to 0, and you know each different call, you're changing it, right? It's not exactly the same thing because we have current and start, they're separate names, but they don't have to be, right? The point is, each time we're removing an element off of the array, essentially, we're going through an element on the array, and we're adding it to the aggregate. So the first time, 1 plus 0 is 1. The second time, 1 plus 2 is 3. The third time, 3 plus 3 is 6. The fourth time, 6 plus 4 is 10. Each time, you're moving to the next element of the array, and you're reducing it by taking that number off and adding it to the aggregate. The end result is just the sum. And that's why I was hesitating to go over this, because if you're not getting filter, you're not getting math, I know that this is mind-blowing. Yeah.
Okay, so then the start isn't actually saying where to start looking through the array, because it's always going through the entire array. Start is just like
The
a
starting
starting value
yes.
of what you're, okay.
Good point. If that confuses anyone, start isn't where you're starting on the array, it's the starting value. To answer Peter's question, you don't always have to start at the first value of the array. You can do what they call slicing. You can take a different part of that array. But start is not where in the array you're starting from. It's the starting value of the aggregate, right? So you
initialize it.
The initializing value for the aggregate, precisely. Okay. How bad? Is anyone getting this?
Yes.
Yeah.
Okay.
Not too bad.
This is, I know this is really complex, and like I said, this is what I think is, your definitely exposure time is a huge part of it. And if you're just now seeing map and reduce for the map and filter for the first time, I know it's a lot. Okay. So we went through that.
Can you use reduce with either of the modes, the conditionals or the loops?
You can use reduce everywhere. I mean, it really, this is what I'm saying. Ed is dead right. Look, this type of stuff has wide-ranging application. It's not easy to understand, and a lot of JavaScript programmers don't understand it and simply don't use it. But if you do know it, it's a huge tool in the shed. There's nothing to take away from it. It's just a lot of work to understand it.
Can I show a different application with my
Yeah, you,
illustrator?
definitely.
Yeah.
Come on up here. Yeah.
Sure.
Different tactic. Let's do
Right.
it.
Okay. So all
Yeah.
of you have heard of cloud computing, and some of you might even know what it means. But basically, it's just a fancy way of saying that you can use a bunch of computers to solve a problem at once. Okay, and those computers are generally managed and owned by somebody else. One of the popular things that you can do, like on Amazon, who's heard of EC2? Okay, Elastic Compute 2 is the pay-as-you-go, rent by the hour, a chunk of Amazon's huge cluster. And yeah, seriously, pennies on the dollar. I mean, you know, for a dime, you can have a computer for an hour. And since it's a dime, for about 20 bucks, you could have 200 computers for an hour. All right? So what kind of problems do you have when you're trying to use a bunch of computers at once? Well, generally you have what are called embarrassingly parallel problems. Problems where you can solve them by dividing them up and handing them out and then collecting the results. Okay? And so, for example, if I needed everybody to determine whether or not a book contained the word carrot, I could rip one page of the book out, hand it to each one of you here, have each one of you scan that page, and then report back to me whether or not the page contained the word carrot. Okay? So you have some sort of a function, okay? And we'll call this function find carrot. Sorry, you'll have to put up with my humor. Okay? And we're going to scatter this out to a bunch of computer nodes on EC2. Okay? Now there's a special way in which you can store information in a cluster such that when you load it, each different node gets a small piece of it, or a shard, or a sliver, or a partition, or whatever you want to call it. Okay? So I store my book into something called HDFS. Okay? And I have it partitioned such that each one of these nodes loads a section of pages of it. Sending this function out to be applied to the data at the data's location, that's called mapping it. We map the function on top of the data. Okay, back when this was an old Lisp operation and you had a list of A, B, C, and D, and you wanted to add 5, you would map the function plus 5 to this list L. Okay, and it would add 5 to all of those. So the point is that once you do that, you'll get back, I found it once, I found it 0 times, I found it 0 times, I found it twice. How do you combine those values? These clustering technologies use the same reduce function. They reduce the results. Well, 0 plus 1 happens to be 1. Okay, so those two are reduced. 0 plus 2 happens to be 2. 1 plus 2 happens to be 3. The concepts of map and reduce are very powerful when you can figure out a way in which you need to apply something to a complete set of data or a complete list of information. Okay? If you structure your programs such that you have items that all need the same operation, map is like shooting fish in the barrel. It's really easy.
And it should be pointed out that the function, like find caret, is a lot less space than like your whole library that you're searching.
Yeah, and the reason why cloud computing has taken off is because we get so much data that moving the data around is more expensive than moving the function around. So we send the functions to the data in most cloud computing environments. They're applied and the results are sent back to us. And that's one of the major things that really makes cloud computing different than some other kind of computing. Okay, is that you're sending the functions to be applied. Just like in the list, which you just moved, it would be sending the item that you're mapping to the data. It's applied on the data. So anybody still not understand MapReduce? Is anybody able to program it in JavaScript? You can work on that part later.
All right,
I can see what it's doing. I can work on the program.
Yeah. There's, we're going to cover this one other piece here because we have 30 minutes, and then, well, hopefully we're not going to take 30 minutes. We're going to take like 10, and then we're going to head out and go drink. Because every night we head out to Cedar Creek. The drinking starts at 9 and usually goes on to around midnight. Everyone is welcome to come. It's part of the festivities. Okay. So the last point is, by the way, anyone have any other questions about reduce before we hit the next topic? And we're just going to cover this one, I think, briefly. Okay. So the next thing is about composability, and what we're talking about here is very simple. You can have, in fact, I'm going to show you this in a slightly easier fashion. You can have a function that takes two functions as an argument, right? So if I have we talked about filter, right? I can say a dot, okay. A takes right down here 1, 2, 3, 4, 5, 6, 50, whatever. I can filter that by two things, right? If I wanted to, I can say something like let k equals, and then I can say here. Let me show you this. Let x equals greater than 5, rather, equals x greater than 5. then I can say let less than 10 equals x. X is less than 10. And then what we can do with that is I can say let good, or whatever you want to call it, equals, and then x. Okay, this is a much better example than they're doing. So we're going to go over this, and then we're going to simplify it when we're done. This is called composability. If I have a function here, let greater than 5 equals, it takes an x, and it simply returns whether or not x is greater than 5. Right? Now for a list like this, 1, 2, 3, 4, 5, 6, 50, that's going to return 6 and 50. I can have another function called less than 10 equals x, and it's going to find all functions that are less than 10. So in this case, it's going to go through 1, 2, 3, 5, 6, right? I can say here, let good takes an x, and it's going to find the result of greater than 5 and less than 10, right? I can compose both of those together into this new function called good. Now here's one of the kickers. You can even create something like and. Let and equals my and, so we don't have a problem here. Let and equals A, D, A and B, right? So I can say good here equals my and greater than 5. That's not going to work. It's let good.
Yeah, there we go.
There we go. A filter good. That didn't actually work. My end, I can say X. Oh. There we go. Okay, so you can create a function here, my_and, that takes two different other functions we've created. Right? The point here is just to show you how far you can take this. We're creating an operator called my. This is not in the book. The reason why I like this is because this is a lot easier for you to imagine. We went so far, we talked about how recursion can do things like looping constructs with counter variables, right? One of the other things you can do with functional programming is this thing called composability. We're composing greater than 5 and less than 10 into a new function called good. And we're doing that with this other function called my_and, right?
Concatenate, right?
It's not concatenating. Concatenating is when you take all of the things from one part and all the things from the other part and you add them together.
Right.
My_and is looking for things that satisfy both of these criteria, right? It's producing a function that's a predicate that's looking for things that satisfy greater than 5 and less than 10, right? So my_and is going to look for things that satisfy this predicate and this predicate. It is in and of itself a function that simply takes a value and returns whether or not both of those is true. I think we can go over this again and start the next class off with it. I don't really, because I think we lost people even before reduce. But this is what the book is referring to by composability, except it goes off into a really weird tangent on it. Does anyone kind of see this and have any questions about this? Or anything else we've covered today?
Yeah, the syntax, I would be able to, the concept I get, yeah, the putting together in syntax and being able to create that would be.
You've got to see it for a while to get it. You know, that's just.
You got like 3 functions.
That's for sure.
going on there. Yeah, it's got to put your school. Yeah, my_and is a function, and then inside of the parameters, 2 other functions.
Right. Yeah. Yeah.
And
We're
then you're filtering those too.
And we can provide them to filter as one thing, right? Good. And the thing that's cool about this is we didn't have to redefine greater than 5, we didn't have to redefine less than 10, and we literally created a function called good with both of them. And we returned it right here. And I know that's ridiculous, matrixy, you know, you're in Inception or whatever, the jokes always fly, but yeah, that's it. It's going to take a lot of time getting used to the syntax, getting used to the concepts and the ideas. If anyone has any questions about it, I'm happy to answer. If not, I'm thinking social time and prepare.
Let's do it.
to learn.
Let's do it.
Okay. Class adjourned.